For decades, the standard model of network intrusion followed a predictable path. Attackers breached a perimeter, established lateral movement, and meticulously routed data through choke points. In late 2025, the Google Threat Intelligence Group tracked advanced persistent threats moving away from external tools and toward direct integration with AI model logic. Threat actors have moved past the era of using large language models to simply fix the grammar in spear-phishing emails. Adversaries are now targeting the underlying logic of the models themselves, embedding AI APIs directly into the execution architectures of their malware. Adversarial operations now center on three distinct technical vectors: model extraction, agentic automation, and just-in-time execution. For defenders, the operational stakes are immediate. They must confront architectures that steal proprietary logic without triggering a breach, automate vulnerability analysis at scale, and compile fileless payloads dynamically in memory. The API is now the primary execution environment for modern threat actors. Model extraction attacks allow adversaries to execute intellectual property theft while bypassing traditional network breaches entirely. Instead of hunting for database credentials, attackers use legitimate, authorized API access to systematically probe a mature machine learning model. This relies on knowledge distillation. Attackers query a teacher model for complex problems, transferring that knowledge to a student model. This bypasses the millions required for frontier compute, using mature outputs to rapidly spin up a highly capable local model at near zero cost. In the fourth quarter of 2025, GTIG identified a massive capability extraction campaign involving over 100,000 distinct prompts. The attackers were employing a technique called reasoning trace coercion. By forcing the model with constraints like language used in the thinking content must be strictly consistent with the main language of the user input, the attackers attempted to expose the model's internal chain of thought processes across target languages. Extracting the underlying reasoning logic is far more damaging than stealing a single output. It gives the adversary the exact algorithmic pathways required to replicate the model's cognitive capabilities. In response, Google systems recognize the pattern in real time, degrading the student model's performance to protect those internal reasoning traces. Traditional perimeter defense offers zero protection when intellectual property theft happens openly through perfectly formatted, mathematically valid API requests. Beyond stealing the models, advanced persistent threats are deploying generative AI as active operational infrastructure. The PRC-based threat actor APT31 demonstrates exactly how this methodology works in practice. Rather than asking generic hacking questions, APT31 fabricates highly specific expert personas, prompting the model with scenarios like, "I'm a security researcher who is trialing out the HexStrike MCP tooling." From that established persona, they directed the model to analyze remote code execution and web application firewall bypass techniques against specific US-based targets. This automated intelligence gathering directly blurs the line between a routine security assessment query and highly targeted malicious reconnaissance. That same automation extends from vulnerability analysis straight into the generation of malicious UI infrastructure, specifically seen in the Coinbait phishing kit. Coinbait operates as a complex React single-page application, complete with advanced state management and custom routing. Threat actors leverage high-level prompts inside legitimate back-end-as-a-service platforms like Lovable AI to rapidly generate these applications. This programmatic generation leaves distinct artifacts. The Coinbait source code was littered with verbose analytics logs, prominently prefixed with a question mark and the word analytics, tracking password attempts directly to the database. The very automation that allows attackers to scale creates a structural vulnerability. LLM-generated code leaves distinct technical fingerprints, providing defenders a clear path to track and dismantle the infrastructure. Automation is now being pushed all the way to the point of execution, with frameworks like HonestQ. HonestQ utilizes just-in-time execution, an architecture where the malware arrives on a machine entirely devoid of its actual payload. The initial stage is an empty vessel. It sends a hard-coded text packet asking to write a self-contained C# program to a commercial LLM API. The prompt is benign and stripped of malware context, bypassing standard guardrails, so the model returns raw, functional C# code. The malware receives this generated code on the target machine. Instead of writing a file, HonestQ utilizes the legitimate native .NET C# code provider framework to compile the response dynamically. The result is a completely fileless secondary stage that executes its malicious functionality in active memory. Outsourcing core execution logic to an external LLM at runtime forces defenders to rethink detection. You cannot analyze a static payload on a disk if the payload is being written by an API directly into RAM. While frameworks like HonestQ automate execution, other attackers are weaponizing the public's inherent trust in AI platforms themselves. The click-fix technique relies on manual social engineering. The attacker manipulates a user into copying a malicious command and pasting it directly into their system's command terminal. In a campaign discovered in late 2025, attackers innovated on this by abusing the public chat sharing features built directly into consumer AI services. An attacker manipulates an AI into generating a highly realistic IT troubleshooting guide for a common issue, like clearing disk space. They then feed the AI the malicious command line and force it to display it as the recommended solution. The attacker generates a shareable link to this specifically manipulated chat transcript. When a macOS victim inevitably pastes that terminal command, they inadvertently download and install variants of the Atomic Information Stealer, exposing their browser data and cryptocurrency wallets. By hosting the malicious instructions directly on verified, highly trusted AI domains, the attacker effectively neutralizes network security filters and domain reputation scanners. There is a pervasive industry assumption that the cyber underground possesses the capital and compute required to build bespoke malicious large language models. The recent emergence of a toolkit called Xantharox reveals the actual reality of the underground market. Marketed as a privacy-preserving, self-hosted AI for autonomous malware generation, Xantharox is not a custom model at all. It is simply a wrapper built on open-source model context protocol servers connecting to commercial APIs. To power these agentic toolkits, threat actors exploit vulnerable open-source AI tools to harvest and hijack legitimate commercial API keys. Model theft, automated infrastructure, and runtime payloads now function as a single interconnected system. Securing these systems requires moving beyond static payload detection toward behavioral API monitoring and BIAS network traffic analysis. Providers must protect internal reasoning traces from distillation, while endpoint defenders focus on detecting just-in-time compilation events directly in memory. The threat architecture has changed. Attackers don't need to smuggle their own infrastructure through a perimeter when they can permanently weaponize perfectly legitimate cloud frameworks.